Okay guys, so reminder that your map activities are due on February 14th. Okay, so make sure that those are ready to hand in to me at the start of class since they're on paper. Okay, there's no submitting at 8:30. Don't come trying to find me at 8:30 and miss your class. Okay, just bring them to class because they're on paper, one per group. Okay, if you're done early, you can always hand it in early if you want to. I'll take it. All right, today we are going to go over kinematics graphs. Here's some good news. It's pretty much all the same as it was in Science 10. We're going to talk about position versus time graphs, and we're going to talk about velocity versus time graphs. We're going to do very little that is any different. Right? Really only one thing different on the velocity versus time graphs, and that's just how to calculate the area underneath a little easier with a single formula. Okay, if you remember doing that from Science 10. So, we are going to review / understand what information can be read from the two types of kinematics graphs and understand that the graphs and their the equations that are on your formula sheet are basically derived from each other. Okay, or rather the formulas are derived from the graphs. Okay, and they're just showing the information in different ways. Lots of those word problems that we did at the very beginning with B equals D over T can be very easily translated to graphs. Okay, it's sometimes a lot easier to interpret them if you're looking at the graph rather than reading a story about some bus that was going forward and backward. Okay. And then lastly, okay, learn how those kinematics equations come from the graphs, kind of where they come from. I'll show the derivations today. All right, position versus time graphs. So, same as in Science 10, a position versus time graph will tell you where the object is at any point in time that is on the graph. Right? So you can look at a position versus time graph and know that the object is at a position of 5 meters north at a time of 2 seconds. Okay? And that later it is at a position of 10 meters south at 12 seconds. You can tell where it is at various points in time. You can read that directly off the graph. Because you can see where the object is over time, you can also infer or interpret the nature of its movement. That is, you can tell whether it is moving forward or backward. You can tell whether it's moving at a constant speed or accelerating based on the shape of the graph. Right? And what we want to get the hang of here is not memorizing what the shapes mean, but rather interpreting. Because then that ability to interpret can be applied to any type of graph, not just a position versus time graph. All right? So, in a position versus time graph, position is obviously on the y-axis, and time is on the x-axis. And yes, we will do a little bit of y equals mx plus b here as well. So a little bit of that linear analysis that we did in Science 10 and that you also did in math. So, on this graph, we've got the position versus time data for a high-speed train. Okay. Initially, right in this first section of the graph here, what we have is that the train is traveling at a constant velocity. Now, how do I know that in this first part of the graph that the train is traveling at a constant velocity? Besides the fact that it's printed right there because someone will say that. Is the line pointed diagonally upwards? Okay. On this particular graph, that means that the position is changing by the same amount every second. Would you agree? Okay. On any graph, a diagonal line angled upwards is telling you that whatever's on the y-axis is changing uniformly over time. Okay, so there's a regular rate of change. In this case, a regular or uniform change in position means that you are traveling at a constant velocity. Okay? In this case, 180 kilometers per hour. Okay? If that line continued, over several hours, we would see that every hour it went 180 kilometers forward, or north, or whatever it happens to be. Okay, everyone follow me there? So any diagonal line is indicating a constant change of y over x. Okay? On a position versus time graph, a change in position over time is velocity. Okay? A constant change is velocity. Now, for this part of the graph here, we see that the shape of the line changes. It becomes a curve. And that curve gets flatter and flatter. So, is now the rate at which position is changing also changing? If the curve is getting flatter, you are going slower. Okay, and you can see on there, they use the word decelerate, something we actually don't use in physics. Okay, acceleration is any change in velocity, negative or positive. We don't use the word decelerate in physics. Okay. But that object is slowing down because it's covering less distance every second. Okay, everybody with me there? All right. Does that also relate to something we learned in Science 10 about the slope of a line on this type of graph? Okay. We just said that if you have a diagonal line on this graph, the object's traveling at a constant velocity. If the line's steeper, are they going faster or slower? Faster. Okay? If the line gets steeper, they're changing their position more every second, okay, than a line that's less steep. Okay? So on this part of the graph right here, okay, during this 0.1 hours, the position changed by this much. But in the next 0.1 hours, it only changed by this much. That means it's going slower. Okay? It is slowing down or accelerating negative. Everybody okay with my interpretation? Okay. Now right here, the line's flat. What's that object doing? It's not moving. Position isn't changing. It's at the same position for 0.2 hours, okay, during that part of the graph. Now, on this part of the graph here, it says it's accelerating. Graph is a curve, and the curve is getting steeper. Yeah. If it's getting steeper, it's going faster. Same reasoning. During this 0.1 hours, the train only goes this far. But in this 0.1 hours, the train goes this far. And in the next 0.1 hours, it goes even further. Okay? A curve, a steepening curve, like this, means you're doing more of y in the same amount of x. Okay? On a position versus time graph, that means you're going farther every second than you did the second before. Right? That means you're accelerating. You're changing your velocity positively. Right? Again, this isn't something that we're memorizing. The reason I'm explaining this interpretation is I want you to be able to interpret graphs in the same way. Right? Look at what the shape means as opposed to memorizing a curve means accelerating, because it only means it's accelerating on this kind of graph. A curve on a different graph means something else. Okay? All right, everybody okay with that idea? And then obviously here at the end, okay, we've got another diagonal line, but this diagonal line is steeper than that diagonal line, which is why the constant velocity is greater during that part. Okay? It's covering more distance every time. Ringing a bell from last year? Okay. All right, now slope calculations. You may have been taught this whole thing, okay, at some point. Okay, sometimes people call it this, rise over run. Okay, you might have been taught that. We don't use that in physics, okay? I mean, we kind of do, but we use it in a different way, okay? Instead of calculating slope with rise over run, we use this. Okay, y equals m times x plus b. All right? Y is the y value of any point that is on your line. So if I made right here, the point I was talking about, this would be y. Okay? What does m stand for? Slope. M is the slope. Okay? X is the x value of that same point. Okay? And what's b?
Y-intercept.
B is the y-intercept. This is b. B is the initial value of y. Okay? It's what y is when x is 0. Okay? Now, if I solve for slope using this formula, I just do a little bit of algebra, I would subtract b and then divide by x. So I would have y minus b over x equals m. Is that basically the same as that? Right? I wrote y beside d2. I wrote b down here. We'll say this is d1 down here. Is this the change in y when I do this? Is this the rise? Okay, and then x would be the run. Agreed? It's still the same formula. The reason we like to use this is this calculates more than slope. I can manipulate this and I can find the time it takes to go, some distance that's beyond the graph. Okay. Similarly, I can find how long it takes to go, or I already said that, to go. I can figure out how far I would go in a certain amount of time beyond the graph. I can calculate things beyond the graph with that formula. I can't always do that with the other one. Okay, so we use y equals mx plus b a lot more. Okay, how many people are familiar with y equals mx plus b? All right, let's look at this graph and do a little bit of analysis here. So it's a position versus time graph. It's showing me where the object is at various points in time. Okay. What's the object doing in part A of this graph? Is it? That's always our gut reaction, right? Like we see a line that's going up and we assume it's increasing. But on this graph, an increase doesn't mean necessarily acceleration. In this case, if I looked at this like per second, okay, well imagine I drew that better, okay? Those two lines would be equal, okay? That would mean that I'm traveling at a constant velocity in a positive direction. Okay, my position is becoming more positive, or it's increasing in a positive direction, and that's why our gut reaction when we look at that is it's accelerating because it's getting bigger. Okay, but in this case, it actually isn't accelerating; its position is getting bigger at a constant rate. Okay, what's it doing in part B?
It's going nowhere.
Go nowhere. Yeah, it's standing still, right? Its position at the start of B is positive 6. Its position at the end of B is still positive 6. It didn't go anywhere. It stayed put at a position of positive 6 meters. All right, what's it doing in part C?
Moving backwards.
Yeah, moving backwards at a
Fixed rate.
yeah, constant velocity, fixed rate. Okay, its position is changing. Okay, in a negative direction. What's it doing in part D? Not moving, yeah. It stays at a position of negative 10 meters for all of D, right? It doesn't go anywhere. Its position doesn't change. Does a horizontal line always mean, regardless of what kind of graph you're on, does a horizontal line always mean there's no change? Yeah, it means there's no change in Y. There's a change in X, time is passing, okay? But a horizontal line always means there's no change in Y, okay? All right, E and F are both showing the object traveling at a constant velocity in a forward direction. In which part, E or F, is the object moving faster?
E.
E. How do you know?
The line steeper.
Line steeper. Okay? Your rate of change of Y is greater in E than it is in F. Okay? The slope is greater in E than it is in F. Therefore, it's going faster. It's changing its position more quickly in E than in F. Okay, quick review of a couple of formulas here. To calculate displacement, we take final position and we subtract the initial position. Okay? To calculate speed, we divide total distance by total time. To calculate velocity, we take total displacement divided by total time, which could also be written like this. Okay, we did those like the first day, so it's been a while since we used them. If this whole trip takes 18 seconds, what's the total displacement of this object? Zero. What's its initial position? 0. What's its final position? 0. Okay? Now 0 minus 0, last time I checked, was 0. So, okay, the change in position, the displacement, is 0. Okay? What would the velocity then be over the whole trip? Zero. If velocity is displacement divided by time, and we just established that displacement was 0, well, then velocity has to be 0, because 0 divided by anything is 0. Okay? All right. What's the total distance traveled here? Remembering that distance is scalar and tells us how far we have traveled in total. Okay, let me ask you a different way. How far did we go in part A?
6 meters.
6 meters. How'd you figure that out?
I mean, you're changing your position from 0 to 6.
Right, you're changing your position from 0 to 6. Okay, so this is 6 meters. What's the change in position here? 0. Okay, so if we went 6 minus 0 to figure this one out, could we do a similar thing to figure out C? Totally could. Okay, in C, our final position is -10. Our initial position is 6. Okay, would this be 16 meters? Right, that's how far I went there. Right, how far did we go in D? We don't, right? We're flat. We're not going anywhere in D. And then in these two parts, I go from -10 to 0, which is how far? Another 10 meters. Okay. Okay, so I went 6, 22, 32 meters in total. Okay. To calculate distance, because it's scalar, you got to do it section by section. It doesn't care whether you go forward or backward, just how far did you go. So you will have to calculate it piece by piece and then put it together by simply adding all the parts. Okay? All right. Assuming again that the trip takes 18 seconds, what's the average speed of the object? Can I use that formula now? Right, I just figured out what distance was, 32 meters. I said the trip takes 18 seconds. Okay, that should give me my answer, agree? Okay, what does that come out to?
1.88.
1.88? Okay, is that ringing a bell? I asked you to do that kind of stuff in Science 10 totally on position versus time graph. All right, something I keep forgetting to do, but I'm going to do it right now. Significant digits, because I keep forgetting to do it. Okay, so rules for significant digits, or why do we have significant digits? Okay, significant digits preserve the accuracy of measured values. They make sure that any math you do with a measured value doesn't suddenly make your measured values more or less accurate than you measured them to be. Okay, and they ensure that less accurate measurements don't make your good measurements necessary, aren't made more accurate, okay, by multiplication, addition, subtraction, that kind of thing. All right, so the first rules for significant digits have to do with adding and subtracting. Okay, if I'm just adding or subtracting two measured values, and let's say that they were 1.23, and I was adding that to 4.5678. Okay, which one of those is more accurate than the other? If I measured both of those, did I measure one of them to a greater degree of accuracy than the other? Okay, the one with more decimal places, right? If I have to add those two measured values together, my answer cannot be more accurate than my least accurate measurement. So when I'm done this, okay, this will be 8, this will be 7, this will be 9, this will be 7, okay, and this will be 5. But I can only keep that much. Now, does that mean I have to round? It does, okay? When I'm doing significant digits, I do have to go, all right, I can only keep to this number, but I still have to round it if necessary, okay? So what I'd actually end up with here is 5.80. Okay? My answer would have 3 significant digits, okay? So when you're adding or subtracting, you simply go by the decimal places. Your answer will have the same number of decimal places as the least accurate measured value. Okay, everybody good with that? All right, how do I know if a value is significant or not? Like, for example, 0 is always the number that's kind of out there, all right? If I have this number, how many significant digits does that number have? It has 4 significant digits, okay? Would I write that last 0 if I wasn't certain of it? No, if I wasn't certain of that number, I'd have left it at 5.25. I wouldn't write that 0 unless I knew for sure it was a 0. Okay? Trailing zeros are always significant. How many significant digits does that number have? 2. Okay? Leading zeros are never significant because you can't measure them. The number I have there is smaller than the 2 numbers that are zeros right now. Okay? There wasn't anything there for me to measure effectively. Okay? So that number only has 2 significant digits because those 2 zeros weren't measured. They're just there to hold the place. Okay? Only the numbers that are there are significant. So, leading zeros are never significant. Okay, if you are multiplying or dividing with measured values, okay, so if I had, let's say, 2.0 and they had to multiply it by 7.358. Okay? This number has how many significant digits? 2. This number has, my answer can have 2. Okay? When you're multiplying or dividing, it is simply the lowest number of significant digits is the number your answer can have. Sometimes that means you might have to put a number in scientific notation. All right, so if you can only hold, let's say I multiply two numbers together, I'm only going to have 2 significant digits, but the answer comes out to 5,378 meters. Okay, how do I represent that to 2 significant digits?
Scientific notation.
That's where I use scientific notation. Okay, right now the decimal point is right here. I'm only going to keep it to 2 significant digits, so I'm going to move it 3 places to the left. That's going to mean 5.3 or 5.4? 5.4, I got to round it up, times 10 to the 3 meters. That is that number to 2 significant digits. Okay, we do that a lot in physics. We use scientific notation all the time because we have to reflect our significant digits and our accuracy. Okay. Now, in physics, rarely do you have a question that is one step. So what if you do multiple things in order to get to your final answer? How do you know what to do with your significant digits? Well, this rule works, honestly, 99 or more % of the time. Write down your givens, okay? If your givens are, let's say, okay, and you're being asked to calculate time, okay? Your final answer can have how many significant digits? 2. That's why we give you a mark for writing down your givens. It will really help you decide what your answer should have. Now, there are situations where we could trick you, right? That could be, let's say I also give you this, and I say it's 1 meter. That only has 1 significant digit, right? But would I use that to calculate time if I had those 3 things? Well, if I don't use it, it doesn't affect my accuracy, does it? Okay, that's one place where people get tricked. Sometimes we give you numbers that you never use. If you don't use them, then they don't matter. Okay, so that comes up once in a while. Okay, yes, write down your givens, write down what you think your final number of significant digits would be, but then double check. Did I actually use that number? Okay, if you didn't, then that changes your significant digits. Okay. Other little tips. If you use a number from the back of your formula sheet, okay, these ones here, other useful constants, okay, things like that, those are considered to be absolute. They are not measured values, they're absolute. They don't affect your significant digits. Okay, so if you take a number off of here, like 9.81, use that one all the time, okay? Numbers that come off of here don't affect your significant digits. Okay, these are all considered to be absolute. Okay, counted versus measured. Significant digits preserve accuracy of measurement. Accuracy of counting is considered absolute. Okay, so a situation that comes up in this course all the time is I'm watching a pendulum go back and forth, and I count the number of oscillations, and I count that it goes back and forth 4 times. Okay, is that a measured value or a counted value? It's counted. If it's counted, it's absolutely infinitely accurate and does not affect your significant digits. That's the rule that gets people in Physics 20 the most. Okay, is not distinguishing between something you measured versus something you counted. Okay, if I count the 10 wave crests go by, I didn't measure that, I counted it. I'm 100% certain I can count to 10. Yeah, I can count to 10. Okay, so I'm 100% sure that there were 10 waves. Okay, that's not a measured value, so it doesn't affect my significant digits. Okay? Questions on significant digits? That's really all there is to it for physics. Okay. All right. I don't know why I still have that one on there. Okay, looking at this graph here. What's the object doing right here?
Accelerating.
Yeah, it's accelerating, going faster or slower? Faster, okay? It's accelerating positively. Its velocity is becoming more and more positive, okay? We know that because on a position versus time graph, okay, how steep a line is tells us how quickly we're changing our position. This curve is showing that the line is getting steeper and steeper. That means it has to be going faster and faster, right? Everyone okay with that? That's interpretation versus memorization. I didn't just memorize it. This means accelerating. I looked at it and went, okay, the steeper the line would be on this graph, the more position I would cover. This curve is steepening. I'm going faster. Okay? It's an analysis thing rather than a memorization. Okay? Now, what is going on in this part of the graph? Actually, let's just say to here. Go away. Okay. Let's say just this part.
It decelerates.
Yes. Okay. It is slowing down because the curve is getting flatter, shallower, whatever word you want to use to describe that. Okay. It's flattening, shallowing. That means we're going slower and slower. All right. What about after the top of that? These are kind of mirror images of each other here. Okay. So on one side it was slowing, on the other side it's going faster. Yeah. Okay, that curve is getting steeper again. And then what about this last part? Is that curve getting flatter? Okay, so is that object slowing? Okay. In fact, does it come to a stop? Does that curve, it looks to me like it gets flat, like perfectly flat there right at the end. Okay, so it'll be coming to a stop. Okay, what is this a graph of? What would accelerate positively, then slow and accelerate at exactly the same rate in opposite directions, and then stop? Yeah. Anything being thrown in the air. Okay? During the first part, during part A, that's when you're actually giving it acceleration. You're forcing it up in the air against gravity. As soon as it leaves your hand, gravity's the only thing acting on it. So it slows it down at 9.81 meters per second squared. When it's at its maximum height, does it stop for an instant? And then it accelerates back down at exactly the same magnitude, 9.81, okay? But it goes faster and faster, and then you catch it. And you slow it down and bring it to a stop. I would never ask you that on a test. It's completely unfair. Okay? To go, hey, what is this a graph of? Okay? It is completely fair for me to say what's happening in A, what's happening in B. That's interpretation. But to guess at what's going on, that would be completely unfair. Okay? Now, here's what you have to understand about curves. Okay, when we say this is a steepening curve, it means it's going faster. Okay, if we remember that on a graph like this, the slope of a line tells us how fast it's going, so the steeper it is, the faster it's going. Okay, at any point on this curve, I could calculate what the instantaneous velocity was at that point. It isn't something we make you do anymore because everybody would have to draw a line on there and everybody would draw it differently. Okay? But if I wanted to calculate how fast the object was going at point A, I could draw a tangent that would touch the curve at point A. That tangent would have a slope. Agreed? Okay, the slope of that line would be the velocity the object is going at that instant. All we're really doing there is making the, okay, let me explain this differently. I'm going to tell you the only thing I understood about university calculus. It was the first day. I didn't understand a thing after that. Okay? To a mathematician, a curve on a graph is like a low resolution picture or video to you on the internet, okay? What can you see in a low resolution picture? They're all square. What do they call it? Starts with P. Pixels, okay? The higher the resolution, the smaller the pixels, okay? So if you're looking at something in 4K, the pixels are so small we can't even see them. Well, to a mathematician, when they look at this line, they see that that line is actually made up of a whole bunch of really small lines that are just getting steeper and steeper, okay? Because that's what a curve is. It's a steepening line, okay? Every little line is just a little steeper than the one before. So when we draw that tangent line, all we did was take the line that exists at point A and make it long enough to calculate its slope. Okay? If you draw a tangent, you touch the curve at that point. You're parallel to the curve. You're parallel to that little tiny line that only a mathematician can see. Okay? Again, it's not something we're going to ask you to do as long as you understand the nature of a curve. That's what I need from you. Okay? A curve is either steepening or flattening. Okay? And every little time interval is a slightly different angle. Okay? All right. Position versus time graph. I have given you the equation for this line. Okay? The equation for this line is y equals 3.85 times x plus negative 0.801. Using that equation, I want you to do those two calculations, please. Let's see what we remember from science and math from last year. Okay? I'll give you a couple minutes. All right, so question number 1 wants me to calculate position. Which axis is position on? It's on the y-axis. Okay, so that means I'm calculating y. Okay, they also tell me the time. They tell me after 1 minute. Time's on which axis? X. So they gave me x, and they want me to calculate y. That's the reasoning I need to go through anytime I get a linear graphing question. What am I being asked to calculate, y or x? Okay, which was I given, y or x? Because I would have to be given one or the other. All right, so for question number 1, okay, I'm simply going to go y equals m 3.85 times x. Can I use 1 minute or do I have to convert it to seconds? Got to convert it to seconds. It's seconds on the x-axis. Okay, so times 60, right? Plus negative 0.801. Okay, so 3.85, okay, times 60 seconds plus negative 0.801. All right, so after 1 minute, this thing will be at a position of positive 230 meters. Okay, everybody all right with that? Okay. All right, so question number 2 is asking how long it will take. How long it will take is on which axis? Where's time? X. Okay, so I'm being asked to calculate x, and they're telling me y is 150. I know that because it says position of 150, and position is on the y-axis. So, in order to calculate how long, I've got to take y equals m times x plus b and manipulate for x. So, rules of algebra say move what's not attached first. That would be b. So I'll subtract it over to the other side. Y minus b equals m times x. I want x by itself, so I divide both sides by m. All right, now I've got it manipulated. Now I just plug in my numbers. 150 minus negative 0.801 divided by 3.85. All right, that's going to take 39 seconds.
So do we not use the rule of significant urgency?
Well, on here, I used the three, actually, yeah, you're right, I should have, it was 39.1, right?
Or, yeah, 39.
I should use significant digits. The numbers I was given were a 39.2, yeah. Seconds. Okay, everybody all right with that? Okay, is that ringing a bell from Science 10 a little bit? Okay, I would have totally given you a question like that on the Science 10 test. Okay. On this graph here, okay, so again, it's a position versus time graph. For whatever reason, there's no label here, and there should be, okay, position in meters. Which object's going faster, red or blue? Red. Why? Steeper line, okay? And on this graph, is the slope the velocity of the object? It is, for a couple of reasons. If I think this out logically before I even do any math, okay, when I calculate the slope, I'm calculating how much y changes over x. Y is in meters. What's m over s? Meters per second. That's a measure of velocity. Okay, the other way I can do this is say, okay, m equals y minus b over x. On this graph, that's final position minus initial position divided by time. I'm pretty sure that's also the formula that calculates velocity. Okay, that, what I just did there, that interpretation works on any graph. You can always interpret what the slope will represent on any graph just by doing what we did there. What's on the y-axis? What's on the x-axis? What is my slope going to represent? Okay, that's the best way to do it. Memorizing what all the slopes represent on all the graphs you're ever going to get in physics is going to be a real pain in your butt. Okay, because by the time you're done Physics 30, that's going to be like 4 dozen graphs. Okay, and you're going to get those confused for sure. Okay, it's way better to just interpret every graph. All right, I'm going to show you that when we get to the velocity versus time graph as well. Okay, here's what I would like you to calculate for me. I would like for you to calculate how much further the red object will go than the blue object if they travel for 1 minute. Okay, so how much further how much further does red travel than blue in 1 minute? Okay, so in order to do this, what do I need to find out for each one of the lines there? I need to find out y after 1 minute. Okay, so if I can find y after 1 minute for each of them, I'll be able to figure out how much further one goes than the other. Okay? So, for the blue line, since I've got the blue marker right now, I'm just going to go y equals, okay, 0.26, that's my velocity, okay, times 60 seconds plus 0.195. All right, so the blue line is going to have a final position of 15.795 meters. Okay, and then for the red object, same calculation. Okay, y equals, this time though, 0.38 times 60 plus 0.115. Right, so 22.915 Okay, and then if I subtract those two, do I have how much further one went than the other? So what's 7.2 meters, somewhere in that neighborhood? Right, 7.12 meters. Okay. Everybody all right with that? All right, I'm going to give you guys a... So, using this graph right here, I want you to answer those three questions, okay? Velocity of each cart. Spoiler alert, that doesn't require much work, okay? Question number 2, position of each car after 12 seconds. And question number 3, how long will it take each cart to reach a position of 50 meters? All right, I'll give you a few minutes to work on those. These are very typical things that you would get asked. Like, let's say, in the analysis of the lab report for the lab we're going to do on Thursday. And this is basically exactly the analysis for Thursday's lab. Okay. Okay, just so you know, this here is in scientific notation, the 9.52 E negative 3. That's 9.52 times 10 to the negative 3. Okay, so it's 0.00952. Okay, if you're looking to punch that in. Okay. So let's have a look at these here. For question number 1, do I have to do any math for this one? No. The slope on this graph is the change in position divided by the change in time. It is the slope of this graph. Okay? So the velocity for the blue cart is 1.38 meters per second. For the red cart, it's 2.01 meters per second. And for cart number 3, it is 3.39 meters per second. Okay, as long as we understand what the slope on these graphs represents, okay, it's pretty easy to figure out what the velocities are without having to do any work. Okay? If I gave you a question like that on a test, how many marks would it be out of? 1. You don't have to do anything. Okay, you just have to recognize that, oh, right, okay, the slope of this line would be the position, change in position divided by change in time. All right, position of each cart after 12 seconds. So it's the same calculation that you're going to have y equals m times 12 plus whatever b is, okay, for each one of those. So for the blue cart, that's going to be 1.38 times 12 plus 9.52 e negative 3. Okay, I'm just putting it in scientific notation in the calculator. All right, so we're looking at 16.6 meters, okay, positive 16.6. So for the blue one, okay, positive 16.6 meters. Okay, for the red one, okay, same calculation, 2.01 times 12 seconds plus negative 0.0524. All right, so for that one, we're looking at 24.1, positive 24.1 meters. And then for the yellow one, 3.39 times 12 seconds, whoop, not plus, times 12 seconds, plus 0.0381. All right, so we're looking at 40.7, positive 40.7. Okay, everybody all right with that one? Okay, and then for number 3, okay, for each one of those, we've got to manipulate for x. Okay, so that's going to be x equals y minus b divided by m. Okay, they give us y, so it's always going to be 50 meters minus b divided by m, okay, for each one of those. So for the blue cart, that's going to be 50 minus 9.52 e negative 3, okay, divide that by 1.38. All right, why do I separate that operation? Why don't I just go right after the 9.52, go divide it by 1.38? If I do, my calculator will do order of operations. It will divide 0.00952 by 1.38 and then it will subtract that from 50, not the same calculation. I want the top divided by the bottom. Okay, that's why I'm separating those two things. Okay, so we should get positive, or 36.2 seconds for that one. Okay, and then for the red one, okay, we'll have 50 minus negative 0.0524 divided by 2.01. And that one's going to be 24.9, which makes sense. It should take less time because it goes faster. And then for the last line, okay, for the yellow one, we would have 50 minus 0.0381 divided by 3.39. And 14.7. All right, questions on that? So that is what you should expect for your analysis for Thursday's lab. Okay? On Thursday, the lab we're going to be doing is very straightforward. You're going to have our little electronic data carts. Okay? They transmit Bluetooth to your phone. Okay? So you will need your phones on Thursday to collect the data from the carts. And all we're going to do is just give the carts a push on a track and record them traveling at a constant velocity for like 2 seconds, if we can get that much data, okay, at 2 different speeds. So we'll give them a little push, and then we'll give them a bigger push, and then that'll be it, okay? Then we'll just be doing very similar calculations to this. It's just gonna be on position versus time graphs, okay? In order to get through all the graphing stuff this week, okay, I am not going to give you the assignment on vectors this week. Right? That also means then that you won't have 2 things that you have to think about doing over the break. You'll only have the lab report that you have to think about doing over the break. Trying to save you a little bit of homework and give you a little rest over the break. Okay, so when we come back from the break, we'll probably do that assignment. You'll get a whole class period for it, and you'll probably be close to getting it done in the class period. Okay? Just so you know kind of what's coming up for you. Tomorrow, we're going to go over velocity. Don't pack up. We're still got a few more things to do. Just telling you. Okay, tomorrow we're going to go over velocity versus time graphs. Okay, again, it's going to be pretty much the same as what you learned last year. Thursday, do the lab. Friday, quiz on V equals D over T and graphing. Okay, for Friday's quiz. Right, and those are the quizzes you'll want to look at. 1, 3, and 4 for practice for Friday. All right, so let's try this one, because this one's irregular. We just did a whole bunch that use y equals mx plus b. I can't use y equals mx plus b for this one because it's not a single linear function. It has a bunch of different parts to it, okay, or what we call an irregular graph. All right, so you got this position versus time graph, okay, and just so you can read these numbers a little more clearly, okay, this is 25 right here, so the value here is 25. The value here is 33, and the value here is 27. Okay, just the y values, because it's kind of hard to see on a graph that small. Okay, and then this obviously comes down to 1, comes down to 2 1/4, and comes down to 3 1/2 there. All right. Okay, give you a few minutes on that, and then we'll talk that one through. Okay, let's have a look at this one here. So for part 1, okay, we want to calculate the velocity for part 1. Well, velocity is displacement divided by time, which is also final position minus initial position divided by time. That's going to be 25 minus 0 over 1 hour. So that's 25 kilometers per hour. And it's positive because it's in a forward direction. Okay, everybody all right with that one? Okay, so for part 2, okay, same calculation. We're still going to use this formula, and we're still going to use final position minus initial position. It's just now it's 33 minus 25, and now it takes 1 hour and 1/4. Okay, so that's going to be 1.25 hours. Okay, so 33, so 8 divided by 1.25. Okay. Not times, 8 divided by 1.25. right, is gonna give us 6.4 kilometers per hour, still moving in a positive direction. Okay, and then for the last one, okay, same calculation again, but this time the numbers are gonna be 27 minus 33, and that also takes an hour and a quarter. Right, that's gonna give us negative 4.8 kilometers per hour, the negative indicating that it's backwards. Okay, everybody all right with that? Okay. Okay, everybody take out their phone right now, educational purposes. This is the app you are going to need on your phone to collect data using our carts. Okay, it's free. Okay. Everyone's just gonna need that app. Well, actually, only one person from each group is actually gonna need that app, but put it on your phone for now, and then if you're the person, you've got it. Okay, so the app is called Spark View, spelled V-U-E for some